Okay, so now we are at Neetra in Italy. It's a factory producing transmitters. They are located in Bali, and this is my friend Marco, who are going to help us with this presentation. And also we have Luca here, which is a professional who are setting up these systems. We have a transmitter here. We have the web interface, which we're going to take you through, and some other stuff. So where you want to start, Marco?
I think the best thing to do at the beginning is to say what is DAB. So DAB is just digital audio broadcasting, so the new standard that soon will replace FM all over Europe before, and then hopefully all over the world. And especially from a technical point of view, DAB is based on co-FDM modulation, which is the same modulation used for digital TV, with the only difference that the bandwidth used for DAB is a bit more than 1.5 megahertz, enough to transport audio data. Our transmitters are based on latest generation LDMOS devices, born for digital broadcasting, so for digital TV and digital radio, because they have the right compromise between good linearity, so very good signal quality, and at the same time capacity to absorb not so much energy from the mains network. And then they have the capability to produce a signal which does not disturb the adjacent channel, thanks to digital precorrection, and also thanks to an output filter, cavity filter, which helps in rejecting the out-of-band energy. That's it, that's the DAB in short.
Okay, so this is the cavity filter, which is produced by another company, from what I understand.
Yes, third party and partner of Neetra since a long time. It is 6 cavity, and it is the standard to allow rejection of out-of-band and to be compliant with the mask filter required by the ETSI official recommendation.
Yeah, and these filters are usually placed inside the racks. So
yeah, depending on the size, can be placed inside, can be placed outside, and Neetra is very good in customizing also the mechanical solution depending on the requirements on the room available in each transmitter station. So it's really a choice of each customer.
You can deliver, you know, a finished product in a rack, all ready to use, plug and play.
Or in an existing rack, we find all the customized size to fit in.
Okay, so now for the next slide.
Yeah. Let's focus on the transmitter we have here. It is part of our Saturn HE. HE stands for high efficiency. It is 500 RMS output, and it is based on the latest precorrection technology, which is a technique, electronic technique to allow high efficiency. It is compliant with DAB+, of course, and it is compliant with TheRadioHub, a platform that most of you listening to me know very, very well. It is equipped with ETI, but also with EDI inputs, both with automatic switching available, because there are 2 ETI inputs and 2 EDI inputs, and in case of failure of the primary input, it will automatically switch to the secondary input. And you can define if to go back to the primary input when it is coming back or not. Very flexible, but we will see later in detail. It supports all the operating modes of DAB, so 1 to 4, MFN, SFN. It is equipped with the latest generation digital signal processing, so it allows digital precorrection. That means, first of all, signal quality, and means also saving power as much as possible.
And the transmitter has internal GPS, which is a good thing. Not many transmitters have such capability.
Yes. When designing this unit, we took care of 2 things mainly. Keeping it as compact as possible. So everything inside, you don't need any additional units, which of course will put additional budget on the overall investment. But at the same time allow the airflow coming in very efficiently and in the very critical sections. So we have a compact but reliable at the same time, because the temperature never increases. We have a very careful airflow design and very careful temperature control in it.
Yeah. So we're going to look inside, because what you just said would make sense.
Yes. It is very interesting to have a look inside, because even people who are not very keen to RF technology now will understand how we could design a transmitter so compact, at the same time so efficient in power efficiency.
Yeah, very heavy fans in the front.
Yeah.
And then
as you can see, are chosen with the best quality available on the market. They are very reliable, because typically when high-level customers ask for quality, they ask for a parameter called MTBF, mean time between failures. And typically this parameter is not generated by the electronic components, but by the mechanical components. So it is very strategic to choose high-efficient mechanical parts, like flowers, as you see. And they are three. This means that we have also guaranteed enough redundancy. If any of them, for some reason, will fail, you will not experiment a complete failure of the transmitter, but you will soon be alerted by our control system, and you will be able to replace the fan without losing customers, without losing audience at any time.
Okay.
Now, let's say
this is the amplifier?
Yeah. The secret of Roherty technology is just here. The 500 watt amplifier is made by two RF amplifiers. Each of them is 250 watt RMS. And there is a big difference to legacy push-pull plus AB amplifiers. Those, until now, were made by the so-called push-pull technology. So a couple of RF devices, one amplifying the negative section of the signal and the other the positive one. Here the technology is totally different. We have two transistors, one operating class C and the other operating class AB. The class AB1 is operating on the average section of the signal, and so it is always on. The other one operates only on the peaks of the signal, and it is on just when the peaks arrive. And that's the secret behind power saving. This technology is thus very good for digital technology, because all digital broadcasting signals have a very high peak to average ratio. So it makes sense to have an amplifier which is always on, and another amplifier which is on just when needed. That's it. You can see they are two of them working in parallel, and then there is a combiner at the output, just creating the output signal of 500 watt RMS by adding the two contributions. Each of them is 250 watts. The output connector is a feeder cable with the 500 RMS signal, which then feeds the output cavity filter here. And of course, the output cavity filter then goes to a dummy load, just to put power to a 50 ohm load and avoid any reflected power. But it's good to have detail of a Doherty technology.
Okay, so now we should have a look at also the user interface. There are two ways to control this transmitter. You have the front display here, a control system, which is inside the transmitter. We also have the web interface that can be used. So let's first have a look at how the controls work on the front-facing display.
Okay.
So explain what is going on here.
The front panel interface is organized in menus. because that's the most user-friendly way to interact with the technicians who always have to confront their lifetime with transmitters. The main menu is made by access to sub-menus which are taking care of modulation parameters, RF output parameters, input parameters, control parameters, and then there is the alarm and log sections which in real time show to the user if there are any failures or if in the past some failures took place, and in any case you can have access to the log of the event, the alarm.
And a control button that works like you just scroll and you press it to enter the menu.
Yeah,
very easy.
smart. So with the same knob you can just browse menus and enter numbers, parameters, confirm, check, change, everything with one thing really. The fact that every parameter can be controlled by the user interface on the front panel is very important because anyone, when working directly in the broadcasting site, will have direct access to the parameters without also having a PC or an instrument, which typically is useful for, let's say, emergency situations. But every parameter you have here on the front panel display is available also by remote with a very nice looking web interface. So you have remote access in a much relaxed way, and also from anywhere in the world. And this is of course strategically thought. In fact, whenever you activate a remote control on the user interface, you cannot have direct access on the static control in front of the transmitter, but you're just allowed to operate by remote.
Okay, so if you're setting up the transmitter for the first time now, what would be your first setup procedure? What would you do in this menu?
Yeah, the main menu, as you see, has inputs, modulation, RF, setup, log, and alarm. So let's start from the input menus. The input menus check for ETI presence and also ETI correctness. And as you see, you are checking simultaneously the presence of both inputs. If any of them is missing, the alarm LED will turn on. It's a red alarm. And you can also check the status. So the type of input present, the bitrate correctness compared to the standard, of course, very easily. Then synchronization. You are working in MFN now. If in SFN you will automatically check if the reference inputs 10 MHz and 1 PPS are present. GPS receiver. As we thought before, we have an integrated GPS receiver, and we can check when connected how many satellites are in operation, in view and in operation. And whenever the GPS is unlocked, it will check if it is already unlocked also in SFN operation or still operating correctly in SFN even if the GPS is unlocked, because we have a long time lock after the GPS failure.
So you basically can control everything from that control?
Yes, absolutely. Every low-level parameters are operated by the front panel menus with this very simple user interface in menus.
Okay.
By the RF menu, you can control the output power, and you can read in real time if any reflected power is present. And the reflected power can be generated by different
faulty cables or improperly adjusted filters like this,
yes,
and so forth.
Yeah. Then In RF mode, you have also the precorrection control.
Yeah, the precorrection. That's an important thing, because for stations that switch over from analog broadcast from FM to digital, this is a new terminology. What is precorrection, first of all?
Yes, the digital signal, as I told before, has a very high peak to average ratio. So it excites the amplifier in a special way that the amplifier will generate intermodulation products, so distortion. To avoid this distortion, you have two ways. One is to change the bias of the amplifier, which is nonsense because it will absorb so much energy that broadcasting would be really inefficient. The second way, of course, the smartest way, is to use the amplifier in its normal operating point, so in this case Doherty way, but at the same time pre-distorting the DAB signal in such a way that it will compensate the distortions introduced by the amplifier. So the combination of the pre-distorted signal plus the distortion introduced by the amplifiers will produce a perfect signal. And the smart thing about this is that all of this calculation is done automatically. So we have DAP, Digital Adaptive Precorrection.
So can we see this in action?
Yes.
So let's see precorrection in action. Okay, so how does this work? Could you explain what's going on here?
Now precorrection has been disabled. And now we can again activate it. And you will see in a very short time the precorrection will be computed and the result would be seen on our spectrum analyzer. This is the final result. So an MER of 36 dB means perfect quality, so means very high coverage. If we disable the precorrection, the result is very bad. It's red. You know, red means not good quality. Of course, a so low MER will not allow good coverage.
So the quality of precorrection is quite significant.
It's fundamental, yes, because it means that at the same power level, at the same current consumption from the network, you can get much higher quality. So better quality, better coverage, with no additional cost for the operator. So it's
Makes
the
sense.
dream of every broadcaster, of course.
Yeah, okay, so you optimize every sense of every part of the transmitter chain, so to use the energy as efficiently as possible.
Yeah. And the other good thing about automatic precorrection is that the operator in the network will not need a so expensive signal analyzer like we have, of course, in our laboratory, because they will simply trigger precorrection and the transmitter
will take care of the rest.
Take care of and optimize the output signal.
Do you need to run the precorrection when you receive a transmitter straight from you?
The transmitter will be delivered with optimized parameters. So you just need to plug and play. No need.
But as long as this option is left on, you are safe.
Yes, because
the rest is automatic.
The smart engine inside.
You would never turn that off. No. So you make sure you have that precorrection on.
There is a digital friend inside taking care of it.
Yes, that's very good. Okay, so that was the look inside.
Probably we made much more than look inside.
Parameter setups.
We already have seen how to set up the main parameters.
Yeah. Now let's have a look at the web control. So, could you explain what we're seeing here on this screen first?
Yes, this is a graphical user interface, which in one shot gives an idea of the main parameters which are important for the broadcasting activity. Here you can see that the transmitter is sketched in blocks. You have the input block where you see the EPI inputs present. Primary and secondary are green. It means they are active, they are correct. the modulation block, the amplifier block, and then the processing block, which includes the synchronization with the output signal for SFN operation. Here, the output section is summarizing all the main numbers: the forward power, the reflected power, the operating temperature, the voltages and currents of each of the amplifiers inside. Then you have single blocks, each of them explaining what is happening for each section. So, inputs, EDI, they are set for automatic switching. They are both present, again, green. Then you can set the modes, TEI mode. You can check what is in the primary and in the secondary ETI input, so the type of the G703 signal in this case.
So could you explain storage time?
Yes, the storage time is the time needed for the input processing section to process the input signal before going to the modulation scheme, so to the real modulator.
Okay, so that adds to, as a delay in the overall transmission?
That delay is only a local delay that is also needed for a correct SFN operation, because let's say the trick inside the SFN modulation is the alignment of all these delays. So when the transmitter receives the input signals and also the reference signals, has all the numbers to compute carefully how much of that delay is used before the modulation, and so align the outputs of all the transmitters in the
So
SFN.
about SFN, if you deliver several transmitters to a customer, would you be able to calculate the correct SFN values if you know exactly where the transmitters are to be placed on the map?
Yes.
Do you have the GPS coordinates?
Yes. First of all, technology today is helping very much, because we have coverage simulation softwares, which, thanks to maps, can create very reliable maps in which you can have into consideration the three dimensions. So longitude, latitude, but also altitude. So you will know in a very reliable way how much of your territory is covered and what is the field level for every part of the coverage. So what you have to do is just to define your target coverage areas, which typically is at this moment in the initial phase is big cities, and then we will find the best antenna systems which will fit the existing towers. Most probably towers are already existing, and then we will try to find the best transmitted powers, which in combination with the antenna elements chosen will give the best coverage.
Yeah, and also setting up the SFN.
And this simulation already includes